relatively straightforward. So today we're going to be looking at antiderivatives. This is going to be our bridge between differential calculus, which is what we did first semester, to integral calculus, which is mostly what we do second semester. So the derivative and the integral are kind of like inverses, that they like one kind of undoes the other one. It's a little bit more complicated than that, but that's the general idea. Okay, so it's like integration is like going backwards from a derivative. So it's trying to recover the original function from the derivative. Right now we're going to call this process anti-differentiation, but we're really talking about the same thing. So we say a function f is called an antiderivative, or I should say a function cap f is called an antiderivative of little f on the interval I if the derivative of cap f of x is equal to f of x for all x on that interval I. So it's the antiderivative if when I take the derivative, I recover that function back. Everybody's okay with that?
So it's just the derivative is just equal to the function?
So we say that cap f is the antiderivative of little f if when I take the derivative of cap f, I get little f back.
Oh.
Okay. Now, what's the immediate consequence of this? Yeah. Right. So cap f need not be unique, right? Because if we take a look at an example here, if this pink one is just y equals cap f of x, and this one is like y equals cap f of x plus 1, if I do the derivative of each of these, I get the same thing, right? So how many different antiderivatives does a function have? Infinitely many, right? Because you can just tack on any constant to the end. It's a different function, but it's going to have the same derivative. That's the plus c part, yeah. So that's where we're heading. So we say if f, or I should say cap f, is the antiderivative of little f on the interval I, then the most general antiderivative of little f is of the form f of x plus c, where c is just some arbitrary constant. So let's do a couple of examples. So we're going to look for the most general antiderivative for each of the following functions. So what is going to be our antiderivative of sine x? Right, so we remember that the derivative of cosine x is negative sine x, right? So negative, or the derivative of negative cosine x should be sine x, right? So our antiderivative here should be negative cosine x plus c, because it wants the most general. So I know that should be a plus c. Chanel.
I didn't understand. So where'd you get the cosine from?
So Christian remembered that the derivative of cosine is negative sine. We're looking for a function whose derivative has a sine in it, right? Because that's what f is, right? Little f is the derivative of big F. So, okay, what function do I know whose derivative has a sine in it? Well, cosine's derivative is negative sine. If I just divide the negative over to the other side, the derivative of negative cosine is sine x. Well, that's my f, big F, and that's like my little f, right? Does that feel okay?
Yeah.
So it's basically all we're doing is trying to think backwards. Brady.
So is this just finding what the inverse of
Yeah, it's just going backwards from derivatives, right? So all our derivative shortcuts, still valid. We're just looking at them going the opposite direction. Exactly, yes. So do we remember a function whose derivative is 1 over x? Natural log of x. Very good. And now I think technically speaking, I think they had an absolute value on the x. Why do I put the absolute value there? Can you do the natural log of a negative?
No.
No. No. All right. How about the last one here? What is going to give us a derivative of x to the n? Braden.
-1.
Yeah, so let's think about it this way here. Let's say that we just do the derivative of like x cubed. We get
3x squared.
3x squared. So I don't have a constant on here at all, right? So let's divide that constant over. Everybody's okay there? So if I want this to be x to the n, that should be n plus 1 over n plus 1, right? So that's our reverse power rule. Is x to the n plus 1 over n plus 1. Remember when we do the power rule, we subtract 1 from the exponent and then multiply by the exponent, right? For undoing that, we're going to add 1 to the exponent and then divide by our new exponent. Does that feel okay? Here's a table where we've just kind of collected some of our derivative rules and rewritten them as antiderivative rules. So like the antiderivative of 1 over x is natural log x, the antiderivative of e to the x is e to the x, et cetera, et cetera, et cetera. Important 2 takeaways here is the constant rule still applies, where I can just ignore the constant, pulls to the front, and just worry about the function. And this antiderivative operation is distributive. So if I have a function with a bunch of terms in it, like plus something, plus something, plus something, plus something, I can just anti-differentiate term by term by term. I don't have to do anything weird, just like we did with derivatives, right? If I have derivative of x squared plus sine x, I just do derivative of the first piece and derivative of the second piece. I can do the same thing with antiderivatives. I can do the antiderivative of the first piece, antiderivative of the second piece, and just go term by term by term, which is nice. Everybody's cool? All right. Let's do some specific examples here. So we're looking for the antiderivative of g prime of x, which is 4 times sine x plus 2x to the 5th minus square root x all over x. So the first part should be kind of clear what to do. What are we going to do with this, though? We're going to do some algebra before we get started. What part of this is making it hard to do an antiderivative of? That it's a quotient, right? So what we should do to start is, instead of writing that as a single fraction, what if I write as 2 fractions with a common denominator? What's the advantage of me writing it this way? I can now reduce those 2 separate fractions because they're monomial, right? So 2 x to the fifth over x just turns into 2x to the fourth. And square root of x over x turns into
X to the negative half.
x to the negative half. Now, let's do our antiderivatives. This looks much better, right? Because now I have a trig, a polynomial, and a power function. All of these I can use normal antiderivative rules. I don't have to do anything weird or fancy. This is very, very common, where some algebra beforehand takes an integral that, or an antiderivative that's like, I have no clue what to do with this, into something that's going to be trivially easy. Very, very common. Even more so than when we did derivatives, where it was usually just a time saver. Here, the algebra takes an impossible problem, makes it possible. So even more important that we're taking a moment and looking for some algebra shortcutting to take an impossible problem, make it possible. Cool? Okay. So we can ignore the 4. What's the antiderivative of sine x? Negative cosine x. Again, I can ignore the 2. What's the antiderivative of x to the fourth? X to the fifth over 5. 4 plus 1, exactly. And then what's the antiderivative of x to the negative 1? Half. X to the 1 half over 1 half.
Wait, how is that the antiderivative for x to the fourth? X to the fifth over 5.
I'm just using this rule.
Oh, got it.
Is that good?
Yes.
Okay. And what are we missing though? Plus c, because it wants all functions. Got to write those plus c's. And then from here, just a little bit of cleanup, and we're done, right? So minus 4 cosine x plus 2/5 x to the fifth minus 2 square root x plus c. Everybody feel good on that? Okay. Let's look at another example here. Notice here we're asked to find f, and then we're given a point on f. What is this extra piece of information going to allow us to do? It's going to let us find the specific c. Because if we know f has to go through a specific point, we know that the c that we pick has to make that possible. So that extra point is always going to be to solve for the constant. So we're going to start the same way. Let's look at this first to see if there's any algebra thing to do. This is no problem, right? But what am I going to do with that?
20 over.
Yeah, I would think about it this way. Why is that helpful to us? That's tan inverse. Yeah, good memory. So let's go ahead and do our antiderivatives then. And I have my plus c.
Wait, so antiderivative of e to the x is just e to the x?
Because what's the derivative of e to the x?
E to the x.
Yeah, e to the x. Yeah. Is that okay? And it's nice, these antiderivative rules are really just our derivative rules recycled, right? They're just going the opposite direction. So if you know those already, you kind of already know your antiderivative rules, which is lovely, right? I love when it works both ways and the new rule is the same as the old rule. Okay. To finish up now, I'm going to plug in -2 for f of x and then 0 for x. And I'm going to use that to solve for c. What's e to the 0 equal to? What's tan inverse of 0? That is 0. So if I just subtract 1 from both sides, c is -3. So my answer should be e to the x plus 20 tan inverse of x minus 3. Is everybody happy? How's this going so far?
When you know, let's just solve for C. Like,
When you're, if you're given a point.
oh, so you just plug in. Oh, got it.
Yep. If you're not given a point, you can't solve for C. If you're given a point, you'll be able to find the specific C. So there would be just one function now that is the antiderivative and passes through that point. Okay. Let's do another. So here it wants f, but we're given the second derivative, and then we're given 2 points along the way. Well, if I look at this, is there any algebra I need to do with that? No, that looks pretty easy, right? So let's start. The antiderivative of the second derivative is going to be the first derivative, right? I ignore the 12. What's the antiderivative of x squared? X cubed over 3. And then I'll ignore the 6. What's the antiderivative of x? X squared over 2. And then what's the antiderivative of 4? 4x. And then I'll have plus c. Now, notice I don't know anything about f prime. I don't know anything about the first derivative, so I can't solve for c here. Okay. Well, I'll just now be taking, well, let's clean that up a little bit, right? That'll make life easier. So it's at 4x cubed plus 3x squared minus 4x plus c. We should have done this earlier. I want to mention one thing here, right? Now, technically speaking, every time we did an antiderivative, we'd have like a separate constant. But what am I going to do there? I just aggregate all those constants together and just call it big C, right? Now, I just want to make mention that that's really what's going on behind the scenes here. Because rather, like just crossing my T's and dotting my I's. Nobody ever writes it with a bunch of separate ones. They just aggregate it all at the end. And did it matter that technically speaking, this was going to be like 4 times C1 plus 3 times C2 minus 4 times C3? No, because those are all just constants also. They all just aggregated into the C. Chanel.
So I just want to make sure, what does the C represent?
A constant.
Okay. Well, like, why do you need to include it for?
Because all of these, remember, are technically an antiderivative of f.
Okay.
Because if I take the derivative of f and I do the derivative of f plus 1, both of those just give us the same thing, right? So these are both antiderivatives. We have to count for all possible antiderivatives. What we do is we just tack on a plus c at the end. Okay. Let's do the antiderivative then of f prime. So just like before, I'm going to ignore the 4. What's the antiderivative of x cubed? X to the 4th over 4. Antiderivative of x squared. Good. Antiderivative of x. Great. And antiderivative of c. Cx. Because c is a constant, not a variable, just a constant. And then we have to have a constant. I'll call that constant d now. Now what I'm going to do is I'm going to use those 2 points to solve for my c and my d. Now, worst case scenario, you might have to plug in both points and create a system of two equations to solve. Here we're much luckier because it's a polynomial and one of the values is, or one of the x values is 0. So if I plug in 0 for x, I just get 0 to the 4th, 0 cubed, minus 2 times 0 squared, plus c times 0, plus d, so d is 4. That's lovely. Because now if I plug the other one, I get 1 is equal to 1 to the 4th, plus 1 to the 3rd, minus 2 times 1 squared, plus 4, c times 1 plus 4. So if I move that all over to the other side, I get negative 3 for c. So my answer should be x to the 4th plus x to the 3rd minus 2x squared minus 3x plus 4. Not too bad, right? Pierce.
Right there where you have d equals 4 to the left of that,
Mm-hmm.
that's plus d.
That's a plus d at the end. That's a d.
Is that c times 1 below it? Is it c times 1 plus 4?
Yes. Penmanship problems, right? I forgot to import the graph for that, so we're just going to skip example 5 because I screwed that up. Example 6 says a particle moves in a straight line and has an acceleration given by a of t equals 6t plus 4. Its initial velocity, v of 0, is equal to negative 6 centimeters per second, and its initial displacement is s of 0 equal 9 centimeters. Find its position function. So remember, the derivative of position is velocity. The derivative of velocity is acceleration. So the antiderivative of acceleration is velocity, and the antiderivative of velocity is going to be position. So we're just going to be starting with that acceleration problem and anti-differentiating back to a position function. Everybody's cool with the plan? Okay. So our velocity function is going to be the antiderivative of this. We'll ignore the 6. The antiderivative of t is, and the antiderivative of 4 is 4t, and then we have plus our constant. To solve for the constant, I know that v of 0 is negative 6. So I know that c is negative 6. So my velocity function is 3t squared plus 4t minus 6. Okay, now we'll anti-differentiate again to get our position function. Ignore the 3. Antiderivative of t squared is?
T cubed over 3.
And the antiderivative of t is?
T squared.
The antiderivative of 6 is? Well, t's really. And then we have plus our constant. To solve for that constant, I'm going to plug in 0 for t and 9 for s of t. And I get that d is equal to 9. So my position function, t cubed plus 2t squared minus 6t plus 9. How's this feeling? Pretty good, right? Not too bad. One more example here. Doing great on time. It says a ball is thrown upward with a speed of 48 feet per second from the edge of a cliff, 432 feet above the ground. Find its height above the ground t seconds later. When does it reach its maximum height? And when does the ball hit the ground? No, it hits the ground when the position is 0.
You just gotta add physics to it.
So find its height above the ground t seconds later. What is it asking for here? The position function, the s of t. So where it's going to be an anti-differentiation problem here, right? What is the ball is thrown upward with a speed of 48 feet per second? What is this? It's our initial velocity, right? Our v of 0. What is 432 feet above the ground? Yeah, it's our s of 0. It's our initial position. So this is kind of like the previous problem, but what aren't we given? An equation for
Velocity or anything.
or acceleration, right? Physics students, what is acceleration near the surface of the Earth?
No, it's negative 10. Please don't use negative 10.
Hold on. What are the unit? What are the units here? Feet. What's acceleration near the surface of the Earth in feet? It's negative 32.
That's what I just recognized the problem.
So there's that. What's the antiderivative of negative 32?
0. No. What?
Antiderivative.
What is wrong?
32x.
Negative 32. Well, we're going to use t's. And then plus our constant. Everybody's okay? So let's solve for c. So 48 equals negative 32 times 0 plus c. So c is 48. So our velocity is negative 32t plus 48. Now let's anti-differentiate that. The antiderivative of t is, and the antiderivative of 48 is 48t. And then we have plus our constant. Plug 432 in. And 0 in for t. So d is 432. So our position function is negative 16t squared plus 48t plus 432. That's the first part. Everybody feel good with how we got to there? Okay. It then says, when does it reach its maximum height? When will that occur? When velocity is 0. Great. So I have 0 equals negative 32t plus 48. So what do I get? 3 over 2 for t. I guess that's seconds. Okay. And then it says, when will it hit the ground? Yeah, so that's s of t equals 0. So I have negative 16t squared plus 48t plus 432 equal to 0. What am I going to do there to solve that? Yeah, quadratic formula. How many answers am I going to get? 2. How do I know which one I want? The positive one. So I think that comes out to be like 6.09. Is it okay that I skip plugging it into the quadratic formula? Oh, no, 6.9. Sorry. That's the gist of it. So what we've gotten today was like a symbolic treatment of how to do anti-differentiation. When we start chapter 5 next week, we're going to be building out the geometric side of this, because just like when we did a derivative, we started just like looking at, like slopes getting closer and closer, and eventually becomes a limit definition, so that the slope is the derivative is the slope of the tangent line at a point. We need a similar definition for an integral or an antiderivative. What does this really mean geometrically, so that we can like prove stuff with it and kind of build some intuition about like, what is this really doing? Because right now, all we're doing is kind of pushing around symbols, and like, sure, we can push around the symbols and figure out like, what was the function that gave me this derivative? And we're pretty good at that already. But like, what's that really doing? So that's what chapter 5 is really going to be the guts of. So for chapter 5, we're going to do sections 1, 2, 3, and 4, and then take the first test. We'll do section 5, and then the following stuff after that. I just felt like that was a good place to do it. So again, we're going to have like 2 sections of just kind of like building out the foundation before we even get to definition for an integral of like, what is this really doing? And then that definition from the integral will feed into what's called the fundamental theorem of calculus, this idea that derivatives and integrals go back and forth, that kind of cancel each other out. But that's where we're kind of heading here in the next week or two. Everybody feel okay?
How difficult is this first test for this semester?
I don't think the symbol pushing and the conceptual side, I don't think is terribly difficult. I really don't. In a lot of ways, I think that the integral side of this is easier for a Calc 1 student than the derivative side is. Now, in practice, integrals are much more difficult than derivatives, because a first-year calculus student can do almost any derivative problem you hand them, as long as it's like a closed form problem. There are integrals that no one can do, that there is no like algebraic way to do them. That in practice, what you do is you do a simulation to come up with an integral value. Now that's way beyond the scope of this class. If you're going to be like a mathematics or statistics major, you'll learn about the techniques to do that. You call it like Markov chain Monte Carlo method, is like MCMC is what you call it. That's the name of the technique you'd use to like simulate the integral. And if you are like, a data scientist or something, like this is a normal part of your daily life, is doing these kind of techniques, because integration in general, really difficult. For a first-year calculus student, not too bad. And in fact, in a lot of ways, easier than the derivative, because going backwards from a chain rule or product rule or quotient rule, it's pretty hard. We'll do a little bit of that here. But like a product rule inside of a chain rule, inside of a quotient rule, extremely difficult to go backwards from. Not something you'd be doing in this course. And then there's stuff that just like, I can write a function, ask to integrate it. It's not terribly hard for me to come up with. It's just impossible there's not like algebraic methods to do it. So in general, integration much harder. But for you guys in a Calc 1 and 2 class, it's actually pretty easy. In comparison to like a derivative problem that has like all these different derivative rules nested inside of it, which can be really challenging to get through. Although you know exactly what to do. It's just a matter of like hanging on to all the detail, which is hard. But you know what to do. There's integrals that just like, there's nothing to do. I don't know, what can I do with this? I can't do anything. So that's kind of where we're heading this semester. So chapter 5 is all like foundational stuff. Chapter 6, we're going to do some application. So like what can I use what kind of problems can I use an integral to do? Your fundamental problems are going to be like accumulation problems. So like how much stuff do I end up getting? And then volume problems. So if you have like a really irregularly shaped figure, how do you calculate the volume of that thing? Mathematically rather than like empirically. I mean, if it's empirical, you just drop it in a tank of water and look at the displacement, a la Archimedes. But like, can you do this algebraically without actually having to have a physical representation of the thing made to see how much volume it contains? But those are kind of like your two main, when you talk about applications, that's kind of the application you're talking about. Or calculating really irregular shaped areas. These are all applications of integrals and stuff we'll be doing in that section. Then we'll do some differential equation stuff. So differential equation is just an equation with like dy dx's in it. And we'll look at some different techniques to deal with that. And then we'll probably do we're going to do a couple of BC topics along the way that aren't something that would appear on your AP exam, but if you're a student that's going to take a calculus course in college, these are things that I would feel bad if I didn't expose you to beforehand. It's kind of the semester. So I think there's less content in the second semester by design because we have less time. And I think in a lot of ways, these topics are easier. I think the hardest topics here are easier than the hardest topics in first semester. Let me put it that way. So, particularly if you have like a good visual imagination, like the volumes is the hardest one because you have to kind of picture, does this thing have a hole in it or not? And like, what do the cross sections look like? Which is not, it sounds hard, but like, it just takes a little bit of practice to like close your eyes and look at the picture. It's like, okay, it's kind of has a hole in the middle. It kind of goes like this, and there's like a circle on top. So all the cross section, like, we'll talk about it when we get there. But it's bad at first, but with a little bit of practice, it's like, okay, they're all kind of the same, which is nice. So yeah, I mean, that's kind of where we're going to be heading. So this is our first dip in the toe into what second semester is going to be doing primarily. That being said, most of these homework quizzes are going to be first semester review topics because I just don't want to get too far away from that in trying to keep us sharp and prepared so that when it comes time to take this AP exam in the spring, it's not like, oh, I have to relearn all first semester, because we're still going to kind of be like going back and seeing things and doing like what we did today, which I don't think was too bad. But it's stuff that like, oh yeah, I need to remember that like instantaneous rate of change is a derivative and average rate of change is a slope, and like how do I approximate something like that from a table or a graph, and take some time to remember how to do that. And you just want to be kind of reinforcing that along the way. But I think hopefully what you found was the stuff that we did today was really easy once you kind of remembered what to do. The doing of it was really easy anyways. And that's should be kind of how the course looks. When we go back and look at these first semester things, they should feel easier after we've had some time to sit on the information, really kind of keep on moving forward. Should feel easier when you go back and look at it, because we're really trying to take a deep conceptual look at these things, which is hard in the moment, but I think like pays a lot of dividends long term. Like things become easier when you go back and look at them if you really are able to understand what it is we're really looking at. So yeah, that's the gist of what we got going. So, questions for me about anything? No exam in semester 2. That's nice, right?
Yeah.
you have to take the AP exam, and I would encourage you all to, even if you don't study for the AP exam, to try. I would feel hard pressed that if you were in class the entire year that you couldn't get a 2 or a 3 relatively easily without doing any additional work. And if you study a little bit, like 3, 4, 5 should be eminently doable. Now, some of you guys, a 3 or 4 doesn't really matter. The 5's the only thing that's going to matter to your institution. But like 5s are pretty doable. You know, like, I don't know, like class last year is, you know, there's like 35 kids, and I think like 5 or 6 of them got 5s. It was pretty good, like pretty good. You know, too many 1s from people that just showed up and didn't, you know, phoned it in. Where it's like you could have gotten a 2 or 3 if you just did the whole thing and tried the whole way through. But I think we took a lot of 0s after the first section, or at the first, you know, section of the test or whatever. But, you know, like 5s are doable. They really are. Like if you have paid attention all year and you are careful and you're kind of quick, you don't even have to be that fast. But if you're fast and pretty good, or really good and kind of slow, 5s are doable. 5s are definitely doable. Yeah, Pierce.
How long is the exam, like total?
Well, it's 4 sections, and I forget what I have it in here in the My Notre Dame here. Let me look. So there's 45 minutes, or there's 45 multiple choice questions broken up into 2 parts for an hour 45 total. And then there's 6 free response questions broken up into 2 parts for an hour and a half total. So that's what, 3 hours and 15 minutes total. And there's a break. Yep. There'll be a break in there. It's not straight through, but that's the format. And your exam date's a little bit later than it was last year. It's May 13th. Last year, I think it was on the 8th.
Will we be graduating or not? But we'll be out of school.
Yeah, you're out of school by then for sure. My personal opinion is I think it's probably better for most of us to have this test the closer we are to the last day of school than further we are away. Because as much as I'd love to believe that we have the discipline to take an hour or 2 every day that we're not in school and like look at this stuff, I don't know that that's really going to happen. I would love you to just have your last day of school and take the AP exam the next day. You know, or a day later or something where it's like you slept in one day, you did some studying, and then you take the AP. Yeah, where it's as fresh as it can be. But, you know, from last year, it really seemed to me everybody that the students that I expected to prepare well and did well did very well, like 4s and 5s. You know, there are a few that were like, oh, you phoned this one in. But I get it, right? Like if you have 6 AP classes, you know, it's like I'm going to have to pick a little bit about which ones I really want to put my energy into because I can't do them all. So I get it. But yes, but we'd have to make an appointment for me.